Stanford University.
I had a dream like 25 years ago in an auditorium like this. And to prevent you from doing the same thing, I thought I'd give you a homework assignment to fill in and help me out. Because I noticed I don't have an agenda slide as the previous presenters did. So because I figured 25 minutes is not really enough time. So if you can fit that into an agenda slide, I can present in 5 seconds or less. I would appreciate it. And if you send it to me before lunch, because otherwise you can't be in line before me at lunch. So let's talk a little bit about eBay and the analytics and the deep analytics we are doing there. And many of you might be wondering, OK, what the heck are you trying to analyze? And basically, we analyze whatever we are doing on the site. And this is just a screenshot from the home page, just to help you understand what the stuff is doing we have to think about. So this home page is owned by probably 30 product managers. And you hear them arguing over, OK, I want to have this picture about twice the size as it is today. And the other guy says, no, then you're stealing from me. I can give you this. Right? And they would argue forever if we would not be able to prove who has the right to go. Or the only other thing I want to point out is the eBay buyer protection. eBay doesn't own a single item, and we have no control over how and when and what is being shipped. But we still stand behind the marketplace and protect the buyer to help build trust. Now, this is a 2-3 year kind of project that allows us to actually offer that. A lot of analysis goes in, and a lot of other feature development is going in that allows us to take on this risk. Think about how to build trust. Well, trusted sellers, detailed seller ratings, all those kind of things that have been introduced over the last couple of years by eBay have been introduced to support these features and maybe others. So I still can't find the right button. So at eBay, as you can think, the website is generating a lot of stuff. And the last 10 years, we've been collecting like transactional data, listings, bids, items, and we stored it, we analyzed it for all that time. But it really hits the fan when you start collecting the application logs. It's like 50 terabytes a day that is being generated in application logs by the site. And in order to process this, get it into our analytics systems, run the applications, massage the data in place, we are touching about 100 petabytes per day in physical I/O, going down to the disk, get it into the CPU, and process all this stuff. And it goes way beyond 100,000 data elements. We have 55,000 batch chains that massage the data in place in our analytics systems. And for the application logs, we have over 100 trillion pairs of information in a table. Our user community is up to 7,500 named users. Oops, that's a secret. 7,500 named users on our enterprise class data warehouse. And they are sitting all over the place in the whole company. Right? It's not just product management. Right? It's business analysts, it's development communities, and so on, who have access to the data. And obviously, it goes around the globe. It goes around different countries and different languages. And we have to provide high-level support 24/7 times 365 on those large systems, which is sometimes a challenge. Because the users never sleep. They're running millions of queries every day and churning over a terabyte per second, just on analytics systems. So we have different use cases for different things, and one system cannot handle everything. That's what we figured out pretty quickly. It all started 10 years ago with the enterprise data warehouse. This was an Oracle port 10 10 years ago, and it grew into two of the 5 largest data warehouse systems in the world based on Teradata. It's about, the only comparison we have across those systems is petabytes of spinning disk. So it's a 2.5 and 3.5 petabyte spinning disk system, 120 nodes, 166 nodes each. This is the place, that's our bread and butter. This is a place where we have the transactional data that's coming in from the site, generated by all the applications, generated by users like you. And this is what we have been using for the last 10 years to analyze and support various applications and support the growth. It's just the regular structured information. Everybody knows who does databases. And the access of choice is obviously SQL. 5 years ago, we heard there is an application log and people would like to analyze this. And it used to be in an ab initio cluster. So now how do we get this into a database? So now we are talking somewhere between 5 and 7 terabytes of data that is being generated just for this. This is just the user behavior information out of this log. We need to get into a database, and we want to keep 2 years or more. So now this meant, well, we got to get to a better price performance point. And we did work with various vendors, including Teradata, and built a system which is called, has a code name Singularity. This is a place, is also a Teradata system, but it's slightly different configured. The enterprise class data warehouse, if you would buy one today, has maybe 180 disks behind it, maybe 600 gigabyte drives. The Singularity system has only 72 disks behind a node, but it has 2 terabyte drives. So this Singularity system has been landed in July. It's the largest database ever built. It's 36 petabytes of spinning disks just for this one production instance. It's a system with 256 nodes. It's 6,000 cores. It's about 500 million CPU seconds per day we can burn on this system. And we already figured out it's not big enough, so we're going to double this within a year. In order to access this is still SQL, because we had to go away from ab initio, where we had to have a developer coding for us the access to get to a self-service, and SQL was the tool of choice. And we actually extended SQL to allow us to access the way the data is being stored in semi-structured form. And we will talk about this. This is the core of this presentation today, is to talk about Singularity itself. And then finally, we have a third system that came out 2 years ago for us in a mainstream kind of effort. 2 years, we started with the 500 node clusters, and within a year, we were the 3rd largest Hadoop user in the world. Today, we have a 1,000 node and a 500 node cluster, and about to deploy another 1,000 node cluster to do, it's always called unstructured, but it's not really unstructured. It's complex data. Thinking about text analytics, thinking about picture analytics to support our business. And as you can see on top of this slide, the user community varies. By far the most user reach you have on the enterprise class data warehouse, with more than 500 people accessing the data concurrently. Any given minute, there are 500 requests starting, finishing, or running at that box. And that's where you find most of the analytics, most of the reporting, corporate reporting kind of stuff. The further you go to the right on the slide, the less concurrency you're going to see. So given the different configuration of the Singularity system, still using the same kind of technology, but different configuration, that's already limiting the concurrency down to 150. And you will see less active users on that system these days. And on the Hadoop side, the concurrency is way below that. So we would see something like 5 to 10, maybe 20 at peak times to keep those systems up and running. So let's talk a little bit about more about the data on how we're going to collect that. So the application is being on the website is generating logs, right? The application servers are writing local to a TIBCO bus, and then and that's all happening within a second. And then we are listening on that bus from the analytics side and filtering out the data we want to have. And we apply minimum business logic like sessionization, or at least the end of session information. And then we use an ingest parallel system to get the data loaded into Teradata. Today, in an infrastructure like this, if you would have to load raw data, we can load about 11.5 terabytes per hour. On the Teradata side, we do a lot of the bot detection and additional massaging in different intervals, every 10 minutes, every hour, every day. And then once a day, we provide the same data to our Hadoop clusters for analysis on their side if an analyst needs it in that form. So what are we going to do with it? So one of the use cases on the Singularity box is actually exactly supporting what I showed on the second slide. It's really allow us to do the A/B testing between different choices we have to make on the site. So one of the examples here is the size of the picture, right? So there were arguments about, okay, should it be larger or smaller? Should I use the same space to provide additional information, or should I just show a fancy, nice picture? Turns out to be a bigger picture is the way to go. And the only way you can really prove that is by running the experiments. So if you are a user of eBay, you are part of that environment. You are part of those tests, and probably even more than one of those tests. But given our numbers, the statistics coming out are fairly good, and we can actually drive that forward. On top of that, we are keeping track of those probably 75 to 100 tests on the website with an application enterprise platform that allows you to define those tests and then analyze those tests as they happen every day. So now let's get to the meat. What is semi-structured? Semi-structured is really structured information. I just don't store it in a normalized form, column by column. What I'm doing is I identify the most frequently accessed kind of columns, and those will be stored in columns. And then I have big varchar fields that allow me to stuff columns in there. And most frequently, it's being used as a name value pair list of things. So, and to go after this, in the first couple of years, we developed fundamental UDFs to actually go after that and filter out the pieces we want. So in this example, it's a name value list that will, I give an argument like which one do I want, which is the item, and I will get the item list. So now what if I want to take this and want to calculate, okay, how many items have been surfaced on the site and how frequently and so on and so on. Give me a ranked list of those items. And so the next step would be take this SQL, stuff it into the with clause for the table function, because this is the data that is being started with. And then I go after this with a normalized list function that allows me to pivot this list, so with those 5 entries, and it gives me back 5 rows. And then I go over this and do my regular group by and order by to get the results I wanted. So now, if I have to do this, right, we have about 4 billion records per day of this application log in the event table. It's about 2 trillion rows next week in about 640-day partitions. And the variable part are about 10,000 different tags we are using. Our site gives out about 40 billion search impressions every day. And the total table is somewhere between 1.2 and 1 point a little bit compressed database space. And the total of the data would be somewhere between 6 and 7 petabytes if it would be uncompressed. We have 135 million items surfaced on a given day out of over 200 million we have. And you know, the top item might surface 70,000 times. How much time would you give it? Anybody? Non-eBay? OK, 32 seconds. Because the time here is really determined how fast can I scan the table. Everything else is already there. right? And then the pivot is not really taking much. Now, given this is a large system, it's 256 nodes. So the semi-structure, we see a lot of potential there. It really is helpful when you have an extremely complicated data model. Think about 10,000 different tags. How many tables would that translate in? And then whenever you get a new tag, you're going to model it new, and your ETL breaks. So on the ETL side, we have less transformations because it's just a var chart. We just stuff it in there. We don't worry about errors at that point in time. It's faster loads because we're loading only one table. And it's better compression, too. So the event table compresses to 84% using block level compression in the database, which is really helping the I/O, as we will see in a bit. And on the processing side, as I said, it's already pre-joined. It's already within the context of the row to get to the information. So it's a very efficient way to go after this. It's just a different way to go after this. And and the interesting thing is a lot of those functions can be done with a single scan of the table. So this is what we've been working on, this and regex functions and all those kind of things we've been working on the last two, 3 years. The new one is really, how do I apply business logic to this environment? And one of the things we are really interested in is analyzing the path people take through the application. So think about 2 different sessions, like the first one is on the web homepage, searching for something, viewing some items, and then bidding. And then the other one is maybe on a cell phone, you have a homepage, you go to My eBay, and you bid on 2 items you already had in your My eBay list. In order to feed that into a visualization tool, I might have different needs on how I want to put that out. And this is just an example. You don't have to do this. But maybe I want to have, identify the home page, identify a search page, identify each individual view item page, or if I have more than one, just ignore the more, just show me one, or tell me in parentheses how often this happened. And if I take this and put it into what we call an XPath function, by identifying the key columns, by identifying the metric columns, and then identifying a regular expression pattern that allows me to say, OK, I'm only interested right now in whoever started with a home page and ended in a bid. And by the way, our home page is page ID 1, 2, 3, 4, and so on and so on. So you can make your own definitions in there. So a highly flexible function that would go and apply not just one function. It can apply more than one function, a whole list of functions. Like in this case, I just spit out the pathing information in 2 different formats. One is a list count, and the other one is a list collapse. And it will give you the data as you see it in the bottom of the screen. But the real power here is, again, it's happening at the speed of scan. And it's allowing me to calculate more than one metric at a time. Now, switching gears a little bit, going back to compression, as I said, compression was very high on the list for us because we needed to store a lot of data on a cheaper platform which comes with less I/O bandwidth, right? And the key was to compress that stuff so I don't need to read that much from the disk, which was block level compression. And by introducing block level compression on the right-hand side of the screen, you see we cut the I/O for our workload in half. Tremendous gains. On the other hand, you see not every table compresses the same way. You can't just expect an 84% compression rate. It really still depends on your data. But you certainly can end up in the high ranges of 75% for a lot of your objects. When you're talking big data and a lot of data, you also need to pay attention to the environment, to your data center infrastructure. So our goal is, over the next couple of months, to consolidate our production big data analytics systems, and this is the whole stack, including all 3, in 2 locations, one in Phoenix, the other one in Las Vegas. And the new thing for us is we combine those 2 locations with a private network link, up to 60 gigabytes per second. This then allows us to really act on it, right? We are not interested in building data mausoleums and starting to store data. We want to process it. So you have Vivaldi, you have the enterprise data warehouse, and you have the Hadoop clusters in those locations, and they're all hooked up with the same link, with the same core switch, sorry. And this allows us to process data at a massive scale. And as you can already figure out, we have 3 systems, and maybe it's not just one system that will solve my problem, it's more than one. So we are big into self-service, we are big into bridging the gap between those systems with a high-speed interconnect. One of the things we are working on, and we have a little prototype for pieces of it, is a Hadoop bridge to Teradata that makes it transparent. I can do an insert into a table and get the data over to Hadoop, or I can run a MapReduce job and get the data in flight fed into my MapReduce job as it happens. Obviously, you don't want to do this for the big data, but you can do it for all the lookup tables and all those kind of things that cause you most of the operational problems. And the other thing we are facing, having those 3 platforms is, okay, which one is the better one? Oh, this one is so cheap, let's go over there and do it only there and get rid of the other one. It's not really that simple. So we worked on a cost model, total cost of ownership of those systems, and Nahum will talk about this after lunch in a lot more detail. But as you can imagine, as you can read here quick out of the slides, different queries will behave different, will have different cost demographics depending on what they try to do. Because you want to use the system that is best for this job to do just this. And this is exactly what we try to figure out and formalize over the next couple of weeks. So at eBay, I think we are very well positioned to support our business needs with those 3 different different platforms, spanning pretty soon columnar, because Teradata is offering columnar implementation as well, by the way, at the same time as regular row tables. And then all the way through semi-structured to the large systems where we can actually handle a lot of our structural needs, and then spanning all the way to Hadoop on the flat file side to help with text processing, data mining, machine learning, and those kind of algorithms. So thank you very much.
For more, please visit us at stanford.edu.